So as mentioned in the email this video is attached to, suppose the height h of a kangaroo's hop after it stretches its tendons a distance x1 beyond their unstretched length is 2 meters. How high would the hop be after it stretched the tendons 10% more than before, a distance 1.10x1 beyond their unstretched length? In a simplified model, we assume that all the energy for a kangaroo's hop comes from the elastic energy stored in the tendons, which behave as ideal springs. Ignore air resistance and other energy dissipation. Well, since we're ignoring dissipation, the mechanical energy does not change. Now we have to include both gravitational and elastic potential energies in the mechanical energy, though. So the first thing I did here, though, was draw a diagram to illustrate what's going on in the problem. As you can see, two perfectly drawn kangaroos. The first one illustrates just before the kangaroo hops, and the second one is after the kangaroo hops, with its height at the highest point. Now again, the mechanical energy does not change, so we get the formula here, which is K sub I plus U sub I gravitation plus U sub I elastic is equal to K sub F plus U sub F gravitation plus U sub F elastic. Now, initially, when the kangaroo is crouched before the jump, it has zero kinetic energy. Now, just because it's a little easier, I chose the initial gravitational potential energy to be zero. And if you think of the elastic potential energy as being stored in a single ideal spring with spring constant K, the initial mechanical energy is going to be K sub I is equal to U sub I times gravitation plus U sub I elastic is equal to 0 plus 1 half kx sub I squared. Now this is where the x sub I represents the initial stretch of the tendons. Now with the kangaroo at the high point of the jump, the kinetic energy is again going to be 0 if it jumps straight up, because the tendons are no longer stretched, so the elastic potential energy is going to be 0. But now there's a gravitational potential energy, and at a height of h above the initial point, the final mechanical energy is going to be our formula here, which is K sub F is plus U sub F gravitation plus U sub F elastic is going to be 0 plus mgh plus 0. Now this is where m is the kangaroo's mass, so setting the mechanical energies equal to one another, I get that 1 half kx sub I squared is equal to mgh, and that is going to be give us the formula here, which is h is equal to kx sub I squared divided by 2mg. Now we don't know all the constants, such as like the mass, the spring constant, and the initial amount of stretch. So what I did here was set up a ratio, which gives me h2 divided by h1 is going to be equal to kx2 squared divided by 2mg divided by kx1 squared divided by 2mg, and that gives me x2 squared divided by x1 squared. Now for a 10% increase in stretch, x2 is going to be equal to 1.10 x1, and that gives me the formula here, which is h2 is equal to h2 divided by which is h2 is equal to x2 divided by h1 squared times h1, which is equal to 1.10 squared times h1 is equal to 1.21 times 2.0 meters, and that gives me 2.4 meters. So using a 10% increase in the stretch of the tendon, the kangaroo jumps about 21% higher.